Aldehydes and ketones are two functional groups in organic chemistry that are able to perform many different reactions when exposed to different reagents. Today we will look at the reaction that will occur when an aldehyde or a ketone is exposed to an alcohol as well as an acid or base catalyst. This reaction is called acetal formation. To begin, we will start with acetone and a simple alcohol. We will use H+ as our acid, but this could be any acid. It is important to note that this could also be a base, but we will cover that later. The reaction will begin with the electrophilic oxygen on the ketone attacking the H+ from the acid in a process called protonation. The carbonyl oxygen now has an attached hydrogen and a positive charge. The partially negative charged oxygen from the alcohol will attack the partially positive charged carbon, and the electrons from the double bond will flip up to the carbonyl oxygen. The alcohol is now attached to the original carbonyl carbon, and it will carry a negative charge on the oxygen. The conjugate base of the acid, or another equivalent of the alcohol, will now deprotonate the oxygen, returning the charge to neutral and creating a hemiacetal. The reaction at this point is now halfway complete. The next step of the reaction can only be acid catalyzed. Even if a base was used in the first part of this reaction, this step must be acid catalyzed. The OH group will next take the H+ from the acid, turning into water with a positive charge. This is called a hydronium. The reaction will proceed by SN1 with hydronium as the leaving group. The carbon will then have a positive charge that is resonance stabilized. This is also called a carbocation. And the partially negative oxygen on the alcohol will then attack the carbocation. The oxygen from the alcohol will now have a positive charge, and the alcohol or conjugate base of the acid will come in to deprotonate. We are now done with the reaction and are left with an acetal. If we look back to the original molecule, we will see that the carbonyl group is now gone, and instead we have two new R groups, each attached by an oxygen. As we mentioned before, the mechanism leading up to the hemiacetal can be base catalyzed. In this mechanism, the H- from the base will deprotonate the alcohol, leaving us with a negatively charged oxygen, called an alkoxide. This will then attack the carbon in the ketone, and the double bond from the carbonyl group will then flip up, leaving us with the negatively charged oxygen. This negatively charged oxygen will attack the H from another equivalent of the alcohol, turning itself into an OH group, and the hemiacetal has been made. Once this step is done, the mechanism will proceed the same way as we showed before, but it must use an acid in this step because we must convert the OH group into an OH2- hydronium leaving group in order to perform the SN1 reaction. Acetal formation is also reversible through acid hydrolysis. By adding water and acid, you can go from an acetal back to a ketone or aldehyde. While we won't go over the mechanism, it is very important to know that this reaction goes both ways, and it will be key in the following situation. One of the most important functions of acetal formation is its use as a protecting group. So let's look at this molecule that contains a ketone, but also has an alkene. If you remember from Orgo 1, H2 nickel palladium platinum will reduce an alkene to an alkane in a reaction called hydrogenation. However, these same reagents will also reduce ketones and aldehydes to primary alcohols. But imagine that you only want the alkene reduced. How do we do that? If you add a vicinal before you add the reducing agents, the vicinal and the ketone portion of the starting molecule will go through the mechanism shown previously and undergo acetal formation. The product of this reaction is a cyclic acetal that is then unreactive with the hydrogen gas and metal, causing only the alkene to be reduced. To remove the cyclic acetal and reform the carbonyl, add water and acid. This reaction mechanism allows for selectivity, which is key in organic chemistry. Now let's look at a real-life biochemistry example. The acetal formation reaction is used in the synthesis of glycosidic bonds that connect sugar monomers into polysaccharide chains. In nature, the synthesis of new glycosidic bonds is catalyzed by enzymes called glycosyltransferases. However, instead of starting with a ketone or aldehyde, sugar monomers in their cyclic conformation are already hemiacetals. Another notable difference is that instead of an acid being the source of protonation that converts the OH group of the hemiacetal into a good leaving group, it's a kinase, a protein that phosphorylates the OH group, thus making it a good leaving group. Once the leaving group departs and leaves a resonance-stabilized carbocation, a nucleophilic alcohol group on the growing polysaccharide attacks the highly electrophilic carbocation. A base then deprotonates to remove the extra hydrogen and an acetal is formed. Once again, this is a simple SN1 reaction. Thanks for watching this video, and we hope this helps you learn more about acetal formation. We wish you all the best in Orgo 2, and don't forget to practice your mechanisms until you know them like the back of your hand. They will really help you on the test. Good luck and enjoy the rest of your year.